Differential equations are how we model continuous phenomena in the world. You might even say that calculus was invented so that we could express and solve differential equations. Many differential equations you come across come from physics, but there are plenty from biology, sociology, engineering, and many other fields of study. The main idea of a differential equation is that it's an equation involving derivatives of an unknown function. So like the kinds of equations that you're used to solving already, in which the solution is a number, a differential equation, when you solve it, you get an entire function out. Now you may mix in some differential equations and some non-differential equations. We usually call the non-differential equations boundary conditions or initial conditions. And sometimes they involve the derivatives too, but they're only at specific points in the domain of the function you're trying to find. Like the kinds of equations you've solved thus far, differential equations might have no solution, one solution, or many. And there are many different ways to solve differential equations. Some of them are approximate, some of them are precise, and over your study of mathematics, you'll run across a few of them. Most of the times, though, an approximate solution is good for applications, but doesn't tell you how the solution will vary. Having an explicit formula as your solution will help you understand how the solution will vary as you change some part of the differential equation. Now, differential equations show up in many, many different places, so let's see a few of them before diving into the mathematics.
Differential equations describe the flight of a ball. Oops. They describe the sound of the vibrating string in a musical instrument and the ticking of an antique mechanical watch. And they describe the temperature of your hastily prepared dinner you forgot to cook this evening. A differential equation is any equation involving derivatives of some unknown function. The solution to a differential equation is a choice of function that satisfies the equation, makes it true. So just as a caution, if you run across the solution of a differential equation, it's a function, it's not a single number. It's a little bit weird to think about functions as being unknowns, but that's what differential equations is about. Now, this is the sort of thing that takes some practice, so let's look at a very simple differential equation. So let's say that the unknown function is y. So solve for y is equal to y as a function of x. So in this equation, it involves the derivative of y with respect to x, and the question is, what function will satisfy this equation? Well, it's pretty easy to find solutions to this particular differential equation, because you'll notice it's really asking the question, what function is 4 times itself when you take the derivative of it? I.e., what function has the derivative which is 4 times that original function? Well, it's got to be an exponential function, and something like y is equal to e to the 4x will do nicely. This is a solution. Notice it's a function. And let's check that this is a function, is a solution. Okay, well, we take the derivative of this function and ask, well, what do we get? Well, I get 4 e to the 4x by the chain rule. And you will notice that e to the 4x has showed up again, so that's 4y. Perfect. It checks out. Now, not every function is a solution, so for instance, y is equal to sine of 4x is not a solution. And this is easy enough to check, because if you take the derivative, again, the chain rule says this should be 4 cosine of 4x, and that is not equal to 4 sine of 4x, which is 4y. So, okay, differential equations can have solutions. Here's a differential equation with its solution. In fact, let me give you another solution to this differential equation. So another solution to this differential equation is 3e to the 4x. Because if I take the derivative of that, again by the chain rule, I'll get 12e to the 4x, but maybe I shouldn't have factored that. And you will notice this is again 4y. So this differential equation has multiple solutions. In fact, it has an infinite number of solutions. You'll notice the coefficient up front didn't really do anything. That 3 was kind of irrelevant. So many solutions. Y is equal to a e to the 4x. These are solutions for all a. It's easy enough to check. The calculation is just the same. Take the derivative. And notice that the same function shows up again. Now, let's pick a specific solution that we'd like to find. So let's add a piece of information to this differential equation. So let's add, in fact, you know what, usually I like to write these with curly brackets, and I like to say, let's find the particular solution that has, I don't know, y of 1 is equal to 3. Okay? So we know we've got a whole bunch of solutions. Is a solution for any a. Let's try to see if we can find an a that will satisfy this additional piece of information. This is another equation. This is called an initial condition. So let's see if we can satisfy the initial condition. So what is y of 1? It's a e to the 4. Okay, and we want that to be equal to 3. So for that to happen, that says that a should be 3e to the minus 4. Putting the pieces together, the solution then is a function still. You will notice there's only one a that works. The solution is 3e to the minus 4 times e to the 4x. You might want to rewrite this a little bit. No harm in so doing. Or maybe even like this. Any of these are acceptable expressions of the solution. But now there's only one solution. With that initial condition. Now, it's beyond the scope of this particular video to explain why I'm able to do this and how I knew that this kind of thing works. But know that it is typically true for most of the kinds of differential equations you'll run across. That is to say, if you add in a bunch of initial conditions, you will reduce the number of solutions that you get. This doesn't always happen, but it very often does. A few more comments about differential equations. So if I have a differential equation like this, this is the equation for a spring mass system. So this is a different differential equation. Just some terminology. You'll notice this is the second derivative, the maximum number of derivatives. Is called the order of the differential equation. First order differential equations aren't so hard to deal with. Second order are the subject of many graduate mathematics classes. And higher order differential equations can be rather involved and complicated to handle. Well, at this point now you know what a differential equation looks like, and at least how to check if some given function is the solution. How do you find the solutions? Well, good luck. There's many, many, many ways that you might find solutions for a differential equation. And not to scare you or anything, but for ordinary differential equations, here's one way that you can go after finding solutions of ordinary differential equations. Yeah, there's a lot going on there. So with that, I will leave you with the idea that it's pretty easy to tell if a function is a solution to a differential equation. Much, much harder to find the function that solves a differential equation.